Our next speaker is my colleague, Greg Smith from Crunchy Data. Greg is like one of the most hardware adjacent big server knowledge guys I've ever had the pleasure to share a Slack channel with. And yeah, his knowledge about performance and how to test it is unparalleled. I'm really looking forward to this. So Greg's gonna be talking about speedrunning the OpenStreetMap osm2pgsql loader. So let's learn about how things go fast. Greg, turn on your sound and tell us what's up. You're still mute.
Hey, there we go. You hear me now?
Can hear you now.
Okay, cool. That's my only technical difficulty. We're doing pretty well for the day, I think. Hi there. So I'm Greg Smith. Thanks for the intro, Paul. We're talking about speedrunning. If you don't know what that is, I'll explain it in a second here. What I want to do first is discover my clicker doesn't work for some reason. Here we go. First off, I just wanted to say that I consider the OpenStreetMap, which I think people are very familiar with here, as kind of one of the most important projects I've ever really worked on in some capacity. I mean, the idea that you can just download the entire planet's map data at no cost and then go build your own applications on it, I think it's just amazing. I mean, I've been a lifetime open data advocate, and what makes me interested in this, when I went and looked at other mapping solutions and I have to go, get a key and I have to sign a license agreement and all this other stuff, like that's not stuff I like doing. I like developing code, and you don't get any of that with the OpenStreetMap. You can do what you want with it. You can host it yourself. You can do whatever you want. And I think that's really great. So the program I'm talking about today, osm2pgsql, what this has is a big file that you download. The original version of it used to be about 125 gigabytes. There's now smaller ones available. And it's this big old XML thing in the old version, and you blow it up and you can end up with a terabyte database out of the whole thing by the time it's all said and done. So I've been running this for 6 years now as a regression test for Postgres, because that's what I do. I work at Crunchy's benchmark lab. We have a couple of benchmark labs. They're kind of focused on various community goals. My coworker Jan runs one that's focused on, the benchmarks that he's familiar with. I work close to storage and close to the CPUs and that sort of thing. And that was the angle I approached this whole thing from. My code gets published to this thing called PG Bench Tools that collects lots of Postgres internals and stuff like that. And what I did over the summer is I made it so that PG Bench Tools can also control osm2pgsql. And so now I can get all the data views and everything that I look at when I look inside of Postgres out of that program, as well as PG Bench. And I've just been collecting months and months worth of data on all that stuff, trying to see how it went. So here's an example of what output from that program looks like. The part that really helps for me, if you look near the bottom rows, I'm doing things like changing the checkpoint timing, and I'm changing fsync and all these other things. My toolkit keeps track of all that stuff for me, so I don't have to worry about making a mistake and not realizing what configuration parameters I changed in between runs. Some of this stuff are just manual notes I added in. This shows kind of the yearly process I go through for Postgres. I'll go update to a new Ubuntu version. If there's a new stable Ubuntu out, I'll, see how much faster that is. This particular one, between platform games and software improvements, hardware improvements, everything else, it was about 40% faster than the version that came before. I was super happy with that. Then I download new data from the planet. It's 22% bigger, and I just gave back more than half the game. I'm lucky if I'm 10% ahead by the time it's all said and done. Speedrunning, if you're not familiar with it, is the idea that you're going to take a game that has some sort of fixed ending to it, and you run it over and over again to try to get the fastest possible time or the highest possible score. I'm a big fan of this scene. I used to run around with people who competed to be the world champion at the arcade game Donkey Kong. you know, so this is fun stuff for me. And I decided, let me see what I can do with this program. osm2pgsql. There's like 7 different operations it deals with that I can benchmark individually or in whole. It loads in nodes, ways, and relations. I know better than to embarrass myself by trying to explain what those things are to this crowd. From a Postgres perspective, it also uses copy, which is the standard Postgres path for high-speed data loading. It uses create table as, which is a good way to do bulk loading where you run a select and it writes it all into a table. That whole stage of the loader creates some regular B tree indexes. And then, of course, the end stage of the whole thing is creating a bunch of PostGIS indexes for the map data. It used to be that this thing was pretty much CPU bound the entire time because a lot of it was index building, and index building only ran on 1 core when I started this. Parallel index builds have greatly reduced how long we spend doing all that stuff. So my numbers have been coming down a lot as that technology from core Postgres has been kind of working its way into the system. Once you get to where you're running this stuff on SSD, which takes away a ton of the bottlenecks, and particularly the kind of fast SSD available now, where I'm at now is the performance of single cores on the processor are the main thing that predicts the runtime for over half the time on this whole thing. Intel Xeon processors have been kind of the standard champions for single core performance. And I've been like running along researching this for my Postgres regression work for years now. Here's an example from my lab. You can see another example from my lab right here to my right. This is one of my benchmark servers. I decided, since I was doing this presentation, to dress it up with a little bit of RGB lighting and stuff. You know, and all the teenagers in my neighborhood compete to have for who has the best RGB lighting build. I always win the over 50 age category. So, you know, I'm very proud of that. I like to show it off. Anybody who follows processor technology knows that these AMD processors, they've been catching up a lot of ground really fast with Intel over the last few years. The one of these in the upper left-hand corner, the 3900X, this is being used by the FOSS-GIS lab over in Germany. They're hosting community resources and benchmarking on that. So I kind of stepped away from looking at that one. That one's really a good one for running these things. So I'm glad they've got that lab going. I have access to a few generations past that, though, and I wanted to bring some numbers up and kind of share them today. You know, from my perspective, when you have a database server, one of the problems is that you do have this balance to get. You know, you want this perfect platform, but you know, some problems you have, bulk loading, ETL, there are stages that you're stuck with a single core. And so you need single core performance to be really high. Multi-core doesn't matter. You can't apply 10 cores to a single core problem, right? But at the same time, you don't want to pay a fortune for a single core that's inefficient. Same thing with all the other resources here. You want memory, you want the memory to have a ton of it, you want it to be fast, but really large memory modules tend to be slower. So you have to pick the right one there. And then for storage, you need a decent amount of storage, over a terabyte for this stuff at the loading stage. Fast storage, of course, is more expensive, doesn't hold as much. So balancing all this stuff out is kind of the real core challenge of kind of all this work. All right, so what results do I get? I'm running this thing in under 8 hours now on the latest AMD processor I have for it. I kind of picked the hardest way to run this program, what old Doom players might call the nightmare skill level. If you don't care about being able to update the database later, there's ways you can slim this down, or actually invert slimming it down, that you can make it faster, but you can't update it afterwards. There's versions that turn off optional features like tagging, indexing, and that sort of thing. I'm trying to do the difficult job and use all the cool Postgres features and extensions that are available to me. I'm pretty happy that I can get the entire world worth of data loaded and up ready to go in under 8 hours. Note there's a highlighted number in the middle. That one index build and the related stuff around it is over half the runtime Planet OSM weighs. So that's an example of an index that I've been spending a lot of time trying to get the build time down for. If you're curious, these numbers in the bottom left here, these are the numbers that come out of PG Bench tools that are measurements of internals and kind of how everything fits together. This, for example, shows me that the settings I picked are doing a good job of reducing write-ahead log traffic. If I'm only averaging 9 megabytes a second of write-ahead log traffic, I've clearly been successful at turning almost all of it off relative to how much the clients are writing. So where does that put us? When I look at the disks that I've got available, the one that gave me the best time from this vendor, SK Hynix. If you've never heard of them, this is what used to be Intel's SSD technology. Their drives are really great. The drive I'm using is rated for 7 gigabytes a second sequential reads and 6.5 writes, 1.3 million IOPS, great stuff. The important number for me then is to notice that I'm hitting a maximum peak transfer rate on this thing is 6.5 gigabytes a second, which is exactly where the specifications for the drive are. And that's really what's important for me for Postgres. If we can keep up with storage and storage advances every year, Postgres is keeping up, we're doing our job. One really important note from this though, the new SSDs are so fast now that if I average them over, say, 5-second periods, like a lot of monitoring tools do, I can't even see the IO bumps. If you look at this graph, I have an average in blue at the bottom. You can't even really tell the thing's writing. It will queue up 6 or 8 gigabytes of data, and then just 1 second, it'll be gone. So I think that as people deploy this technology, we might have to start taking the monitoring systems and dropping them to 1 second resolution monitoring. And also maybe do a better job of aggregating out that we always keep track of what the maximum for a second was instead of just losing everything into averages, because data like this, averages gets to be really deceptive. So what do we know about tuning this? There's 2 tuning guides for this thing that are floating around out there. There's one in the documentation, and there's one where people share reference configurations. There's 3 standard tweaks for this. Use one of the types of inputs, use temporary flat file for something instead of using the database. It's all good stuff. And then there's a dedicated node cache for the program that it uses. And the general advice is decrease any other memory parameter if instead you have the option of increasing the node cache and making that faster instead. So I tested all those assumptions and they pretty much bear out. The first one, the PBM files thing. PBM is a protocol buffer binary format. It's just massively faster. When I started this research, I was lucky to get the first part of this, the node part, in there in 5 hours. With the new protocol buffers format and the latest CPUs, I'm getting it in 8 minutes. I just scale shift this chart to even get all the data in there. So it's really fantastic. AMD's latest CPU generation, in particular, they adopted some of Intel's hardware acceleration for memory moves and stuff like that. It's the advanced vector extensions. That stuff is really working well. And when I do like completely synthetic benchmarks, some of them are coming in at like 74% better. Really, AMD, I think, is finally caught up with Intel's lead and is really becoming just a great processor to run Postgres on in this generation that just launched back at the end of September. Memory budgeting, as I was just mentioning, You have static memory you give to Postgres. This does improve if you can get that up to 48 gigabytes. It kept improving the whole way. There's kind of some inherent scaling issues in shared buffers. Some other people have even noticed them. 48 gigabytes gets to be a little kind of where the things roll off. So we don't want to go higher from that. The node cache rolled off for me above 50 gigabytes. I stopped seeing increases for it. And one of the nice things about this data set is that you can move the node cache to maintenance work memory in the database. Once the first 3 stages have finished, node cache goes away, that you can kind of reuse that memory for that. So here's how that worked out for my 2 systems. On 128 gigabytes of RAM, the bigger servers, I could bump that cache up to 50 gigabytes. I gave almost all the memory, 36 gigabytes to it. On the smaller, faster systems, that worked out well. I always built 2 indexes at a time in the queue, because there's one really long index and a bunch of smaller indexes that turned out to be the packing that kind of got everything in there the best for the tests that I ran. At least some people report slightly different results there, but that's we'll continue to poke at that. Postgres server, that this is all pretty standard stuff, other than the sizing, increasing, how much space the write-ahead logging has to play with, and this giant size work memory for this index building stage that's in this thing. I ended up with 8 gigabytes of shared buffers for 64 gigabyte server, and 32 gigabytes, which again is another thing other people have noticed. It's kind of where the bang for the buck starts to roll off for shared buffers. Seatbelts. There are some things that you can do with bulk loading that are bad ideas in regular Postgres. You can turn off synchronization to disk. These things are all fine. Do these when you feel like it. Your bulk load will get corrupted if things fail. That's all normal. There's 2 controversial things I've noticed. I turn off auto vacuum for my tests. I get about a 4% gain out of it. I consider that a standard trade-off for bulk loading. It turns out not all hosting platforms for Postgres even let you do this anymore, which I think is strange. If you can't turn auto vacuum off, but you need that, you can use a workaround of just turning its settings down to almost 0 and kind of starve it of resources to do the same thing. The documentation for the program suggests keeping auto vacuum on. Like I said, it's controversial. Full page writes, you definitely get about a 1% bump on Linux turning that off. The thing is, though, that's not really intended to be a user tunable setting. It's really a platform specific thing. If you have the platform that takes advantage of it, there's big gains. I would not recommend regular users just ever tinker with that one. It's a pretty small gain unless you're on the exact situation you need. And if you ever accidentally deploy a server with full page writes turned off, there are all kinds of like silent corruption issues you can get into. You want no parts of them. Please don't tinker with that one unless you really, really know what you're doing. All right, background writer. I used to work on this code. I know it pretty well. This example here I have running. I tune the background writing up to where it's chugging out about 170 megabytes a second, so the foreground doesn't have to deal with it. This is great. I do want to improve the background writer soon, because I think this has hit the kind of effective upper limit for this setting. You just disable it though, that's fine too. The background writers worries about foreground versus background responsiveness, and there is no foreground background responsiveness to worry about on a data load, so it's not really actually all that important. I just wanted you to see some settings just to see the thing operate. So performance versus growth, where do we kind of see things after 6 years of doing this? The data has gotten 2.5 times bigger during that time period. The loading has gotten at least 8 times faster. So the programmers working on all this stuff, applause all around. Everybody doing work on PostGIS and these loading programs. We're keeping up with hardware. We're taking advantage of hardware acceleration and even doing big re-architecture like that node restructuring with the protocol buffers. So that's all great. For my benchmark test, I did have to dig into this really bizarre trimming topic on NVMe. Some examples of that just to document it. On Linux, I had to tune read ahead and CPU governor. Again, these are all basic Linux tuning things that pretty much everybody does if they really care. I also added swap. I didn't play with huge pages, even though we use it on Crunchy Bridge and recommended in production because mine's just a small single user system and I can't even really measure the impact of the parameter in that context. So here's how all that kind of wraps up. I know that if I tweak Linux, I can get about 6.5 gigabytes per second out of it with the settings. And I know that my drive is capable of about 6.5 gigabytes of writes. And when I showed you that graph earlier, I saw I was getting 6.5 gigabytes worth of random IO. So we're doing right as expected. Postgres is more than efficient enough to keep up with this workload, saturate storage. The performance guides are all pretty good. There's some tweaking I'd like to do. I can publish all that stuff easily enough to get that information out to everybody. What do I do next? After this, it recently became possible for me to run this on the Mac. Some of these tools like osm2pgsql I have running on my Macs now. I want to test out Apple's latest chips. Also, the testing of this thing has gotten me just hours and hours of benchmark data at 1 second resolution. It's 32 gigabytes of time series data. I've always wanted some time series data to test things like partitioning in Postgres or, time series extensions to Postgres, but I never had kind of a free data set that I was happy with. Well, I basically created one now with this whole osm2pgsql project. So maybe we get some more research from me in the future as a result of all that. So that's what I got for you. Good news as far as I'm concerned, and I'm happy to go into questions and whatnot from here, Paul.
Sure. Thank you very much, Greg. We got a couple questions on the Q&A, one from Raj Talati. Do we have any benchmarks for Postgres PostGIS between Intel and Graviton/ARM/?
We do not. We are definitely doing that on Crunchy Bridge. We've been doing work trying to optimize for Graviton because there's some very inexpensive workloads we're able to offer on that product. So we're doing the work, but the Graviton instances perform fine, but they're not really aimed at kind of giant problems like this multi-terabyte data set. So I do want to publish numbers on that, but that would be kind of a separate thing than this talk. But the numbers are fine. And we're, like I said, we're actually have some of them deployed into production now for paying customers. So, I mean, that's a statement right there, I think.
Yeah. This is from Phil Barty.
I see the question. I got it.
Okay.
So the reason that the wall rate was so low is I was basically turning off all the wall logging with the Postgres configuration settings. I was telling it this is a standalone system. I don't need to write raw for replication. And what Postgres does is in acceleration, if you know that if something crashes in the middle, you can just throw it away and start over. You don't need write-ahead logging. You can just skip it. And then if it crashes in the middle, you throw it away and the write-ahead log data just reverses the whole mess out. Because of that rate, on this benchmark, there's no sense in putting the write-ahead log on a separate disk. Now, if I was doing this in production and I had RAID volumes and whatnot involved and I had to replicate it across a bunch of systems, now I'd have to start doing tests like, do I need to put the stuff on a write-ahead log or another disk or something like that? I tried those tests though for this talk and I didn't really gain anything from it, again, because I'd driven the wall rate so low by basically cheating. and tuning it out of the test just to try to see how fast I could get the planet in there.
And yeah, so before I let you go, I have one question of my own, which
Go
is,
ahead.
so you've been using, and it's kind of cool, you've been using OSM as basically a workload all across a number of years in the regression lab. And I was wondering, have you caught any regressions as a result of the OSM regression suite?
I have. Paul's loaded the question because he knows I have, because one of them I reported to him. I caught a regression this year where one of the Ubuntu packaging sets was not working right at all. And what caught it was when the performance tests, when they ran, it didn't come up with it. I also caught a bug in PG Bench last year that was caught by this framework we're putting in there. Postgres code is super reliable and well tested. The performance regressions tend not to really find a lot, but it's really important to me that we do the work and kind of install a broader safety net for the Postgres developers, so that if some code goes in that has a giant backward step due to some accident, that we have automated tests that'll do that. And the kind of long-term goal for my lab is to automate all of these tests I've been talking about today, and all the tests I do, so that they run and people other than myself can go check up on the results.
Awesome. Couple on the chat. What file system are you using?
I'm using just basic ext4 for everything. The file system testing, that gets into stuff like that full page write stuff I was talking about. If I was doing this on ZFS instead, I could then turn full page writes off and actually still have a reliable database that didn't cause problems. It'd have atomic writes and all this other good stuff. This is not really what I was aiming at for this thing, though. I thought answering the question of how fast can you get it with just like the basic, very well understood, very popular ext4 was kind of the most interesting question. And I haven't really been able to get better results on the newer platforms just yet anyway. I did some XFS testing that was more or less the same as ext4, but that's kind of where that's at right now.
Thanks. I think that's it. If you won't mind hanging around the chat and sharing a little more knowledge, if people have some more questions, that would be super duper.
I will.
And David Bittner is on deck.